Continuing our discussion of meso versus not meso, we're going to label our molecules as achiral. Here's a molecule that's achiral. We'll call it molecule number 9. And some of you are saying, oh, that's easy. It's achiral because it's got a mesoplane. Ladies and gentlemen, the mesoplane only works for molecules that have multiple stereocenters. This molecule is just plain old-fashioned achiral. Why is it achiral? Because it's identical to its mirror image. If I drew another water as a mirror image to this water, kind of a waste of time, but here it is. If I was a slightly better artist, you would see quite simply that they superimpose and everything matches up. You want me to make my water a bit bigger? There, everything's matching up, right? That means they're identical. If they're identical, you're gonna they're achiral. If you're identical to your mirror image, you're achiral. Okay? Because you don't have a mirror image. All right, so achiral, and this next one, I hope it's clear. It has a mesoplane right there in the middle of the molecule. H sees H, Br sees Br, and stereocenter sees stereocenter, and propyl sees propyl. And what did I say about R's and S's? There better be as many R's as S's in a meso. And if you quickly do the R's and S's, that's true. So the next one, I'm not even going to try to visually look for a mesoplane. It's not drawn in a way that you can compare the groups. They have to have bonds sticking in the same direction. And I don't have this rotating molecule ability. So I'm just going to use some facts that I know. If it's meso, it has as many R's as an S's. It's clearly got the same groups on each stereocenter, right? Want me to list the 4 groups? Hydrogen, bromine, propyl, and then CH2, and then rest of molecule, which is identical from this stereocenter's perspective, CH2, and then rest of molecule, HBr and propyl. So this thing is also R. This thing is not achiral. I can tell you right now, you can rotate as many degrees as you want. You're never going to get things to match up. If you have all S's or all R's and not a match of R's and S's, there's no way it's going to be meso. So I'm just going to go with CH. This one was achiral due to meso is the first one. This one is chiral, just straight up chiral. Now the beautiful thing about the Newman projection is that you can rotate back carbon -60, rotate back C -60 degrees. And here's what you get. Front C stayed the same. Bromine is now on behind a bromine, potentially meso. H is in front of H. And methyl moved there to here. I mean, that is the definition of meso right there. Look at the picture. I got a bromine in front of a bromine. Where's the mesoplane? Between the ball and the carbon behind the ball. Okay? There's a carbon behind the ball with an H, a Br, and a methyl on it. Okay? The Br sees a Br, the H sees an H, the methyl sees a methyl. There you go. It's this example again, isn't it? Mesoplane right there. Except you started by looking at it from head on. Mesoplane right in the middle. Okay? So achiral due to meso. And ladies and gentlemen, don't do much work on the next one. You do realize they're going to rotate I mean, this doesn't have to be done if you look at the previous example, because groups aren't going to be on top of groups. But I'll rotate front C 60 negative. Front negative 60. So back carbon stayed the same. And then the front carbon negative 60, the bromine's on the bromine. But the H is now in front of a methyl. And the methyl's in front of an H. That's not meso. Methyls and H's are different. H does not match methyl. Methyl does not match H. The thing is chiral. This one's going to get you. Some of you are saying, just take a mirror. I'll take a mirror and cut right through the middle of the bromine, the middle of the bromine, the middle of the H, the middle of the H. But the problem is you're wasting your time. This molecule doesn't have a single stereocenter. Whoa. Yeah, do we agree this group on the top is the same as the group on the bottom? Yeah. So it's just achiral. Garden variety, like for the same reason as water. I can, but it's a waste of time. That's only to cancel stereocenters across from the molecule from each other. There are no stereocenters. This group is identical to this group for the stereocenter. They've reached the same place after going through the same elements, right?
The number 6 is the same.
6 is the same then, yeah. Yeah. No stereocenter. I'm going to say AC, what's my achiral due to meso is M. Want to see the plane? And there's no meso plane in this one, right? Bromine is not the same as H. Bromine here not the same as H, so that's just straight up chiral. Oops. Stereoisomers is normally, and finally, she answered her question from 20 minutes ago. Number of stereoisomers. Equals 2 to the power of n minus 1 for each meso. Wow. Because meso doesn't have an enantiomer. Okay? Number of stereoisomers. So for a chiral molecule, forget about mesoisomer. Mesoisomers are achiral. Okay. So for chiral ones, it stands to go 4 of those minus 1. What? 2 to the power of 2. I'm going to do 2 to the power of 2 minus 1. What am I doing? I'm doing the second part of the question, part B. But I didn't do a good job, so I'm starting over. B. 2 to the, that's A. 2 to the power of 2 minus 1 equals 3. Now, this one, you're saying, how come, Dr. Whitaker? I'm going to answer that question to the 2 minus 1. Isn't the molecule to the left, the one in part, the first molecule listed, an isomer of this molecule? Yeah, one of its isomers, meso. Correct? Right there. If one of these had ended up being S, then this would be meso and would be the same as that. Okay? So the isomer to the left is meso. So here's two isomers. There's this isomer and there's this isomer. They both are 3,5-dibromooctane. It doesn't matter up and down. Molecules are rotating all the time. We can't keep track of all these things. If you can rotate to get a hypothetical situation where there's a mirror plane, then that molecule is meso. But don't waste your time doing that. Use the quick clues. How do you know one, it's a potential meso candidate, even if it's drawn like this? It's potentially meso because it's got two stereocenters, identical groups on each one, bromine on each one, H on each one, propyl on each one, the CH2, then the rest of the molecule on each one, and the rest of the molecule is identical. Okay? So potentially meso. Now, check the R's and S's. If you have an equal amount of R's and S's, it's meso. If they're all R or all S, they're not. Okay? And that's the way to do it instead of, I'm gonna have to rotate the molecules and see. I mean, some of you probably could do this and see this without doing the rotation. I can almost do it now. So that's after years of practice. But, you know, and doing R and S on Newman is a nightmare. So with the Newman, go ahead and do the rotation. That's the beauty of the Newman, is to be able to quickly get to here and to here. And the answer to both of those is the same, 2 to the power of 2 minus 1, because one of them is meso, this one. Nope, B 2 to the 2 minus 1, C. The next one, you're kind of looking at the two isomers. Number of stereo isomers. No. You can't ever say 0 because you're actually looking at a molecule. So by definition, there's one, the one you're looking at, right? So there's at least this isomer and this isomer. So what would happen if you put the bromine from here down to here? You switch them? I think it's the same as this molecule. And yeah, this, you can't even do 2 to the power of n. There's no stereocenters.
N is the number of stereocenters?
Yeah, oh yeah, I never explained n. N equals number of stereocenters. I'm glad you asked that. So in all my molecules here, I picked 2 stereocenters.
So if 2 to the 0 and 1, you only
2 to the 0 equals 1, and there's the answer. I love it. And you're looking at it. How do you like that? My only problem is now, those two are isomers of each other. So we're wrong. They are, do you agree they're isomers of each other? They're both 1,4-dibromocyclohexane. I could say they're geometric isomers. So I'm not going to go with your 2 to the 0. Don't do the 2 to the power of unless they're stereocenters. It keeps you out of trouble. Okay? These are a pair A, B. A pair of cis-trans geometric isomers. You know what that means, right? Geometric isomers. Cis and trans are geometry isomers. That's it. So I guess the answer is 2 for both of them. B, 2, and just write cis trans. 2 cis trans. We got them both here. They are isomers of each other. I don't know if it's a great activity. It was a decent activity. I wouldn't be looking for a test question like this though.
All right.
If you haven't seen it on any of the old tests, which you won't, then you won't be seeing it on a new test, which you will not see.